Okay, so the last topic into this part 1 of chapter 7 is conditional expectation, and also a little bit about conditional variance. Okay, so far we have defined expectation variance, covariance, correlation, and all that. And now we're trying to also bring it into the conditional space, like what we had done in the past. Remember, marginal and then joint and then the conditional. Okay, so for conditional expectation, actually not pretty complicated. Okay, we start off, let's say, with the discrete case. Okay, so the conditional PMF, which we covered in chapter 6, is that remember we're writing x given y. Okay, so y is the conditional. Okay, and the condition being it's being conditioned. Okay, so we know that we're working with all of the cases of the marginal when py is greater than 0. So by definition, we know that the conditional distribution of x given y is, in the discrete case, the probability of x equals to x given that y equals to y. Okay, and we know it's going to be the ratio, right, of the joint PMF over the marginal PMF. Okay, so from there, the conditional expectation. Okay, so again, because y is being conditioned. Okay, so the conditional expectation, we're talking about still the random variable, which is x over here. Okay, so if you read this carefully, the conditional expectation of x given that y equals to y. Okay, so this is really, we're going back, right, to the conditional PMF definition, and then combined with that, combine that with what we know by expectation. Okay, so expectation, as we know, right, is x given y equals to y. Okay, so the conditional PMF, we write it over here. Okay, and then the random variable is still x. Okay, because y is given. Okay, y is known. Okay, and then remember, in that case, it's only single variable, right? And then for a discrete case, we're just doing a summation of all of the possible x values. Okay, so in short, we can just write it out as the summation of x times the conditional PMF. Okay, so again, this is defined to be the conditional expectation of x given y. Okay, so x, okay, is still the random variable, but now we add the condition that y equals to y. Okay, so, but then expectation definition works very similarly in the past. Okay, so the expectation, let me actually just write it out so we can see the connection, right? Okay, so this is when we are only dealing with the marginal. Okay, so the marginal expectation of x, right, is the sum of x times px, okay, of all of the possible x values, right? Now we don't have px anymore. We don't know the marginal distribution of x, but we know the conditional distribution of x given y. So that's why we replace it over here, and then that becomes what we mean by the conditional expectation of x given y. Okay. Similarly, for the continuous case, not too more complicated, honestly, we have the conditional PDF defined to be the ratio, okay, of the joint PDF over the marginal of y in this case. So if you're working with the conditional expectation of x given y equals to y, then you have, as what we had earlier, right, you have the integral of x times the conditional PDF, and then you integrate that with respect to x. Okay, so also, if you remember from chapter 6, whenever we're writing this in the continuous case, right, we know that the probability of that, right, is 0 because y is a continuous random variable. Okay, but remember what we're dealing with is the fy, right, and then the fxy. So they're not 0 per se. Okay, notice that we have to make sure that all of the marginal is greater than, like the marginal we're considering here is greater than 0. Okay, so in that case, we also define the conditional expectation of x given y. Okay, and then of course, if we recall what we did before, right? So when we are only working with the marginal expectation, okay, we know that it's x fx dx. Okay, so here we don't have fx, but we have fx given y. Okay, so we are able to get the expectation of the conditional distribution over here. Okay, conditional random variable here. Okay, so notice how we're writing them as well, right? We're writing them as expectation of x given y equals to y. And that's what the right notation should be, okay, for a conditional expectation. Alrighty, so the properties, okay, of what we know before, okay, about expectation is going to remain. Okay, so if you're working with a gx function, okay, which is a function of x, okay, then if you want to know the expectation of its conditional distribution, gx given y, then it's the same as what we did before. Instead of x, we have gx over here, and then you multiply with the conditional PMF. Okay. Similarly, if we want to know the conditional expectation of gx given y equals to y, okay, then it's an integral for the continuous case for gx times, right, the conditional PDF, okay, and then you do that integration with respect to x. Lastly, okay, remember we also care a lot about sum of random variables now because we might be working with different different random variables, and then we're interested in the sum of them. Then we also have this expectation of sum of random variable results over here. Okay, so what we're doing, as you can see, is that remember we have that result, right? So the sum of the expectation of the sum, right, becomes the sum of the expectation. Okay, and don't forget we don't need them to be independent anyway. Okay, so that property, okay, remains here for the conditional. So if I'm interested in the expectation of the sum of xi given y, then it's the same as taking the sum of all of the expectation of each xi given y. Okay, and I would also like to draw your attention to how to really think about what this is doing for us. Okay, so all of them, like I said, compared to the properties that we know about expectations, they remain. Okay, but everything now is phrased in the conditional sense, right? Where you need to conditioning on the value of y itself. Okay, so the condition x equals to y, y equals to y here. Okay, you can think of it as, say, taking expectation of the random variable x or gx, for example, on a reduced sample space of consisting only of the outcomes which y equals to y. Okay, so in the past, if we're not working with any kind of condition, right, we only have x, for example, then we're taking expectation on any kind of space that x can be. Okay, but now, okay, we are having this new condition of y. Okay, so what we're really doing in some sense is that instead of taking the expectation of x on the entire space of where x could be, we're only taking the expectation on the reduced space, okay, where y has to equal to y. Okay, so right now I guess it could be a little bit vague, okay, but as soon as we start doing exercises like what x could be, what y could be, I think things will start to become clearer. Okay. All right, there's one very, very important result here, okay, is computing expectations by conditioning. Okay, we have this very interesting looking result over here. Okay, so let's take a moment to think about what this means. Okay, this is the important property of conditional expectation. Okay, what this is telling us is that we are able to, okay, when conditions are good, what we mean by this equation is that we are able to get the marginal expectation of x, okay, through the conditional expectation of x given y. Okay, there are certain things needs to be done in order to make this to work. Okay, so what we're doing over here, okay, so remember this inner expectation E, okay, x given y, right, is when y equals to small y. Okay, so for the discrete case, okay, let's just maybe without worrying about why this is what it is for now, let's just think about the discrete case, like just think about how we're going to do about this. Okay, so the discrete case, okay, expectation of x, if I'm just focusing on the expectation of x, the marginal expectation, okay, and let's just say that I happen to know, right, the conditional expectation of x given y, okay, and I also know, okay, the probability, the marginal probability of y. Okay, so when I do this too, okay, and then I'm summing over all of the possible y values of it, remember whenever you're summing over the other variable, right, you're getting the marginal in some sense, right? That's how we're thinking about it in chapter 6. Okay, so what this is telling us, okay, is that in order to get the expectation of x, okay, I can do something similar to like a law of total probability, in a sense that if I know the expectation, the conditional expectation of x given y, okay, and then I also know the probability, okay, of each of the possible values of y, I multiply this too, okay, and then I sum over all of the y, I will get back to my expectation of x. Okay, so this is like, so let me erase over here, okay, this is like a weighted average, okay, but what's important here is that the weighted average that we're doing is the average itself. Okay, so that's why I highly recommend you to think about, in this case, when we're doing this, is to think about the expectation of x given y as a random variable. Okay, and what this does, as you can see, is that now we are weighting this with the marginal probability of y. Okay, And then once we sum over y, we got rid of y in terms of, you know, the condition to some degree. So we're back to the expectation of x. Okay, so now if we come back to this, what this is showing us, okay, is that the marginal expectation of x, okay, can be obtained by doing a expectation of the expectation of x given y. And in particular, okay, the outer expectation, the way that I'm doing it, we're doing it over here, is in terms of y. Just like what we're doing over here. Okay, so let me slow down it one more time. Okay, the left-hand side here is the expectation, the marginal expectation, right? Expectation of marginal of x. Okay, the the right-hand side, as we can see, is a nested expectation. Okay, inside we have the conditional expectation of x given y. Okay, outside we have another expectation. If I want to be super accurate about what I mean by those two expectations, one thing I could do is to add, remember those subscript, okay, to indicate what random variable I'm working with. Okay, so the inner one, remember, y is given, right? Y is being conditioned. So the inner expectation is with respect to x, and that's what we did before. Okay, the outer one is with respect to y. Okay, so what this is saying is that, well, I have the inner one of the conditional expectation of x given y. Okay, and now I'm trying to take an expectation with respect to y, so I'm able to get rid of y altogether to get to my right-hand side, to get my left-hand side to get the expectation of margin of x. Okay, and that's what this discrete case is telling us. Okay, so the intuition I wrote over here, I was trying to explain it, but let's go over it one more time as well. So this nested expectation, okay, or condition, like computing expectations by conditioning, that's what we mean, is a weighted average of the inner conditional expectation where the weights are the margin of y's. Okay, and that's exactly why we mean by the outer, right, this one, the outer expectation is with respect to y. Okay, and that's why in practice you are doing this for the discrete case. Okay, and like I said, it's similar to the law of total probability. Okay, if I want to know the probability of the marginal, like the probability of event E, okay, remember what we covered is that if we have a partition, right, of f, okay, and then if we have the margin of f, right, we multiply that to get the joint of E and Fi, right, and sum over all of the possible Fi's, then we are back to the marginal of E. Okay, so similarly, we're doing something like that here. Okay, lastly, you might be wondering what the conditional, what the discrete case would be, continuous case would be. And this is very straightforward. Following from this part over here, we have the conditional expectation multiplies with the marginal PDF of y, integrate with respect to y, we come back to the expectation of x. Okay, so again, it's very important, like I said, to think through what are these two expectations are about. The inner one is about x, because x is a random variable, okay? And that's what we mean by conditional expectation. The outer one is about y, because we are trying to use the marginal distribution of y, then we are able to get rid of y in the conditioning in order to get the expectation of x. All right, so let's come to an example. Hopefully everything will come clearer, okay? A miner is trapped in a mine containing 3 doors. The first door leads to a tunnel that will take him to safety after 3 hours of travel. Second door is another tunnel, okay, will return him to the mine, okay, unfortunately, after 3 hours of travel. And the third door also will return him to the mine after 7 hours. Okay, so I guess only the first door is going to work for this miner, okay? If assume that the miner is at all times equally likely to choose any of the doors, probably not a really valid assumption. I mean, if I remember, I chose one in the first place. Well, let's see. Yeah, if I chose the second in the first place, I come back, then I know I shouldn't do that one again, right? But anyway, for simplicity, we're assuming that the miner is at all times equally likely to choose any of the doors. What is the expected length of time until he reaches safety? This is not an easy question, okay? So I would recommend you maybe take a pause before you continue watching the video to think through what you would do, especially now, as you know, we're talking about everything under conditional expectation here, okay? All right, so let's get started. Okay, so if we use use X, let's just say use capital X to denote the amount of time in hours until the miner reaches safety, and then let's just use Y to denote, okay, which door he's gonna choose, or he's gonna initially choose, let me put it this way. Then our goal, right, is to find the expectation of X, because X is the amount of time in hours that the miner going to reach safety. Okay, so to do that, okay, expectation of X, okay, we know. And let me just write out that conditional expectation result that we talked about. So because of that, you probably will see that why we want to define X and Y in the way that we talked about. Okay, X is the amount of time, okay, and Y is the door that he initially chooses. Okay, so Y will be 1, 2, 3, right? The cases. Okay, so the conditional expectation, right, in the discrete case, as we know, right, is you will have to, right, do the sum of, I guess in this case, the expectation of X given Y, right, and then Py, right? So if we put it into this context, what we mean is that the expectation of X given Y equals to 1, that's the first door, right? And then multiply with that probability, plus the expectation of Y equals to 2, multiply with that not marginal probability, and that with 3 with that marginal probability. Okay, and one thing we do know, right, it's equally likely to choose any doors, right? So the Y equals to 1, Y equals to 2, and Y equals to 3, the probability of each is going to be 1/3 every time. So we know that expectation is going to become this. Okay, so remember, we're using this result, okay, but in a very specific case, in the condition, in the discrete case where we also have them equally likely of the marginal. All right, so I think this is still like up to this point, we're still applying what we have learned, okay? And next, I think is a little bit challenging to think, so I would still also recommend you to pause if you want to figure out how to go next. And if you have done some thinking already, what I want you to think about is that, well, even though it looks a little bit complicated, this exercise, but one very important result that we do know, which is hidden in the question, is that we know that expectation. So this one is still probably okay. The expectation of the X given Y equals to 1 is 3, because 3 hours travel, right? What's interesting here for the second and the third is that we need to realize that the expectation of X given Y equals to 2, that's choosing the second door, right? Because choosing the second door, what that means is that, well, it just adds 5 hours to the total number of hours that for this miner to reach safety. Okay, because that 5 hours travel is useless, right? Because it's going to return him to the mine. So that's why, very importantly for the second two, okay, we have the conditional expectation of X given Y equals to 2 is 5 plus the expectation of the marginal, okay? And then similarly for the third, it's 7 plus expectation of X, okay? And because of that, we have one equation, right? One unknown of expectation to solve. So expectation of X becomes 15. Okay, so like I said, the first part over here is using the computing expectation use conditioning. Okay, the result that we presented just now in the discrete case. Okay, and then the second part over here, like I said, is kind of challenging. Okay, to think through. Okay, especially just think about how that 5 and 7 can contribute to how we're thinking about the conditional probability, conditional expectation, how we can express it. And then once we figure that out, it becomes an algebra problem, which gives you the expectation of that to be 15. Okay. All right. So a couple of final comments here. We can also compute probabilities by conditioning. Okay. So here we can think about E as a arbitrary event. Okay. And then we're going to define an indicator for random variable X. Okay. As E occurs if X equals to 1. Let me put it this way. If E occurs, then X equals to 1. Okay, if E does not occur, then X equals to 0. Okay, then expectation of X, okay, becomes the marginal probability of E. Okay, and the conditional, right, expectation then just becomes the conditional probability of E given the condition as well. Okay, so this is related to what we talked about in the past. Okay, thinking about this indicator random variable, thinking about from in expectation to probability. So in that case, if you have the discrete case, then you can compute the marginal probability by doing exactly what we did before. Okay, now instead of expectation, we have probability, and then this is the margin of y, right? We sum over with respect to y, so we are able to get rid of the y altogether, so we get the marginal probability of E. Okay, and this is related to the law of total probability, just like what we did before. Okay, and then similarly on the continuous case, you're doing integration. Okay, so this will become handy, I think, when you work on exercises. Okay, and then the key here, like I said, is to think about x as an indicator function. So the probability of the event itself becomes the expectation of x. Then whatever we know about the conditioning expectations and stuff like that can be turned into this probability calculation for those events.